Hello and welcome to the Are Cats Liquid and Other Science Questions podcast. I'm here with John and we're going to be answering questions from you, the viewer, from Reddit and from things we come across in day-to-day life. Hello John, how are you?
I'm good, how are you?
I'm really good. So what's your first question then?
So my first question is actually from Ask Physics, who asked, if you skydive in the rain, does the rain hit you in the face or hit you in the back?
Oh, that's a good question.
So, we had a wee look and we figured out the maths behind it a little bit. So, as you may or may not be aware, if you jump out of a plane, you don't accelerate forever and ever and ever.
No, because there's air resistance, right?
Exactly. You hit a thing called terminal velocity, right? Whereas the drag force from the air will balance out and give, and your speed eventually hits a constant. You don't accelerate forever and ever. So, we looked up what these terminal velocities are. So for rain, that's about 15 metres per second. For a skydiver, that's about 55 metres per second. So
Whoa,
as you can see,
it's actually going quite a lot faster than the rain then.
Yeah, that makes sense, right? A skydiver weighs a lot more than the rain. It makes sense that a heavier object can get faster because the balance of forces.
Right, yeah, because you've got the the weight, which is a force, right? It's pulling down on the person, and you've got the drag, which is
so imagine
stopping the person from going faster.
A brick weighs, see a brick exerts 10 newtons.
Uh-huh.
It's going to take a drag force of 10 newtons to reach terminal velocity.
Yeah.
Whereas we take a feather that exerts a force of 0.1 newtons, it's only take a smaller drag force of 0.1 newtons to get terminal velocity.
Yes, yeah, and the drag increases with velocity.
Indeed it does.
Right, so the faster you're going, the more drag you're feeling. And you can see that in like racing cars, you can see it wherever. So you need to get to a certain speed where the drag is balancing out your weight, your gravity.
Indeed. And then that's when you reach terminal velocity. So, there's essentially, I envision 3 scenarios in this question.
Right,
the first scenario being, imagine both the rain, the water, and the skydiver both start from rest, i.e. they're both not moving, and then they both move at the same time. Okay,
so you look at a cloud and you're like, oh, that
you're
cloud
in the clouds,
is about to start raining, so I'm going to jump out as the droplets are falling. Okay, right?
So it's essentially, it's almost a good analogy, starting at the bottom of the cloud, for example. So what would happen in that case? Well, firstly, as we so said, they both started at rest. So we both jump out the plane and we do the magic button that starts the rain. And then initially what will happen is both the rain and the skydiver both accelerate. And now it only takes the raindrop at 2 seconds to reach that terminal velocity of 50 metres a second.
Right, because it's so weak.
Yeah, because it's so light. And eventually, once it hits that 50, it doesn't get any faster. That's why rain doesn't murder you in the street. Because you're walking around, the rain has came, 1,000 feet?
Yeah.
But it doesn't murder you. It only hits you fairly gently, I suppose.
Yeah.
Anyway, so it'll take about 2 seconds for the raindrop to reach 50 metres a second. So eventually what will happen is the skydiver will actually remain more or less completely dry because the rain isn't touching them as such, per se.
Yeah.
So very quickly though, once you reach past that 2 second mark, you'll find the skydiver will start to overtake the rain and they get rain to the face. The rain doesn't hit their back, but it'll hit their face because eventually the skydiver will eventually go faster than 50 metres a second fairly quickly.
And so you'll be accelerating past all the rain.
Yeah, so you'll be literally falling into the rain. Your front will get wet, but your back should remain dry.
Ah, okay.
Which is interesting enough. The second scenario is essentially, imagine that you're essentially flying in an airplane through the rain. So the rain's already going more or less at its terminal velocity. What happens then? Does the rain hit your back, front, left, or right? Again, the rain is going initially at 15 metres a second, so that's the terminal velocity. We jump out the plane and we have to accelerate. Initially, we're starting at 0. So between your speeds of between 0 and 15 metres a second, you will get rained on the back because the rain is going faster than you.
Yeah.
Yeah, but I said very quickly, you will catch up in that rain.
So basically, like the first 2 seconds.
For a very brief moment, you will not get any rain on your front or back. For a very, very brief moment when you're going 50 metres a second.
Yeah.
As soon as you go over that 50 metres a second, you get rained in the face.
Yeah.
So then it comes again, you're getting rained in the face. So essentially, if you jump out of a plane in the rain, your back and front's going to get wet.
Yeah, but your front will get more wet than your back.
Oh yeah, absolutely. Your front will get way more wet than your back. And that brings up the interesting point of just how hard in the face are you going to get hit by this rain.
Oh, I can imagine.
So we worked this out, and it turns out the difference in speed is actually equivalent to 90 mph.
You'd be getting hit in the face with 90 mile an hour.
The rain going 90 mph, yeah.
That's really sore.
So you said you were on a roller coaster with this happening.
Yeah, so one time I was on the Britain's tallest roller coaster. It's the big one, the Pepsi Max ride at Blackpool, and we went in pretty light rain, like it was drizzle. They usually close it when it's rainy because it's like dangerous. But we went in drizzle, and honestly, it felt like needles were hitting my face. And how fast is the big one? You said it's 75 miles an hour?
Yeah, it was about 75.
And that was drizzle hitting my face at 75 miles an hour, and that was so sore. It felt like my face was burned afterwards.
But bearing in mind, there's much more dynamics than simply getting hit in the face with water. It's cold water, which is more the problem.
Yeah.
I mean, let's think of another scenario. You could 90 mile per hour rain isn't going to cause you any damage, I don't think.
No, it would hurt, right? But it's not going to cause like actual damage.
It would. Yeah, I think it would hurt, but bearing in mind, rain is really light.
So that's
the momentum is nothing.
No,
I think you want to avoid that.
Yeah.
I'm pretty sure I remember reading somewhere about hang gliding, and that should be avoided being done in the rain as well.
Yeah.
I don't know how true that is, but I mean, unintentionally could easily get the rain in your face. It could happen, right?
Yeah.
So moving on to our third point, what happens if you jump out of the plane while it's not raining and it starts raining while you're in the free fall? Do you get wet? Well, unsurprisingly, the answer is you will not get wet, because as long as you're faster than 15 meters a second, which you probably will be very quickly, the rain will never catch up to you until you hit the ground. Then you get very wet. So, yeah, that's more or less the three scenarios I could come up with in terms of skydiving. So the conclusion of that was, essentially, your front's more likely going to get mostly wet. Your back might get wet initially. But it's your front that's going to get wet if you skydive in the rain.
Oh, clever.
Yeah.
I like that. And then also another thing to think about skydiving is that, we were talking a lot about the drag coefficient of skydivers, and they can change their drag coefficient really easily when you're skydiving. So you always see in like action films and stuff that to catch up with other people, they like dive head first into the wind, or if they're normally skydiving, they sort of put their arms up and their legs up and they're kind of belly flopping. That would change your terminal velocity a lot by doing that.
Indeed it does.
And then also, you quite often in films, this really annoys me, is when people like then pull the parachute in films, it's always portrayed that they like blow up, they go back up in the air.
I suspect it's not portrayed that way, but it looks that way.
It always looks that way. But what happens is that they slow down very quickly.
Isn't that what's happening?
Well, exactly. That's what's happening physically, right? They slow down. They're going fast, open up the parachute, and slow down, but they're still moving down the way.
Yeah.
But often, the way it's portrayed in films is that they move the parachute and then shoot upwards off the screen. And that's not what happens. They're not shooting upwards. They're still going downwards.
That's not... I see what you're saying, but I don't totally agree with your conclusion. So, they are still moving down. Yeah, but the camera's moving down like 50 times faster.
Exactly.
So it looks like that's what's happening.
But exactly. But the way that commonly, it's a common misconception that
I see what you mean.
You go up.
I see, understand, yeah. No, they certainly do not.
Exactly. So that's something that I always also think
about. It's not like a rocket ship.
No, exactly, right? What's the propulsion pushing them upwards? There's no propulsion.
But yeah, right, I do know what you mean, because when you look at it, it does look like the camera's almost stationary and it shoots up, but that's absolutely not the case.
So that's another thing to think about.
I guess it's just a dramatic, cool thing for Hollywood, right?
Exactly. So, no, that was a good question.
Thank you very much. Ask Physics.
Yeah. Right, so my question now, this one is from your friend Nikki, asked this question, and he said, if time travel was a thing, how do you think it works? So I had to do quite a lot of research on this, because first of all, I had to work out physically if time travel could be a thing, right? Because I have lots of opinions on how time travel works in movies, or doesn't work in movies, and what my opinion of time travel is. But I want to talk about the science of time travel, right? Because first of all, time travel, moving forward in time or skipping forward in time in inverted commas is actually really easy, right?
Skipping forward in time being faster than 1 second per second.
So I can age slower than you and arrive in the future as a younger person than the world being aging, right? The way you do that is either by traveling very, very fast, close to the speed of light, compared to someone else, or flying past something that's very, very heavy, like you, John, or like a black hole or something.
Essentially, being a gravitational field.
So
not really to fly by, so it's be in a gravitational field.
Exactly, because heavy things or things that warp gravitational fields warp space-time, and space and time are linked by the speed of light. So however fast you're moving, even if you're moving close to the speed of light, in your frame of reference, the light is moving at 3 times 10 to the 8 meters per second, right? And that is why, according to me, time is contracting. So time to other people is moving faster than I'm moving. So 4 months to me might be 4 years to you if I'm moving at the speed of light, right? So while like physically it's not very possible, mathematically it's entirely possible, and we've observed it in like astronomical.
Well, you're saying it's physically proven this does happen.
Yes, yeah, but like for people moving forward in time, we're not there yet. Like in terms of
I'm not really sure biologically.
Yeah,
because that's kind of what we're asking, how this affects things. Yeah. Because light, the time in this special relativity, which is what we're talking about, is defined as, the length of time it takes for a photon from to go to A to B.
Yeah. Well, time is linked to space-time, by the speed of light, right?
Yeah. But my point is, we're talking that time slows down here, and when you go close to the speed of light, time slows down for a person on stationary looking at someone on the speed of light, as you know, time slows down. For the person looking into that, it looks like they're observing. If I was stationary, Steph is going close to the speed of light. I look at Steph, and to me, it looks like Steph is aging slower. It looks like that she's contracted, she's smaller along the direction of movement, and also it's like her mass has increased. But for Steph,
you're calling me fat.
I'm sorry. I was going to say thinner instead of like contract. It looks like she's thinner but faster. But but for Steph's point of view, the opposite is true. It looks like I'm the one who is slowing down with time. Is that correct? Because it's all about your frame of reference. You're essentially stationary, and I'm moving around you.
Yes, but then if I was to reverse my speed and come back to where you are, I would be the one that would be younger, and I've
If you just go from A to B and then call me up from B and ask you tell me what your age is, you would be younger in my frame of reference.
Yeah.
But your frame of reference, you would still have aged the same amount.
Yeah. And then if I was to come back to you, having travelled at like 99% the speed of light, I would not have aged, but you would have.
In your frame of reference, you would have aged the same amount, no?
No.
You're
no. If I travel away from you at 99% the speed of light, turn around and come back to you,
that's correct. So in the stationary frame of reference, which is where I am, yes, I would interpret you as being aged lower, less.
Which is why, in Endgame, probably slight spoilers here, Captain Marvel hasn't aged at all from like the 90s from her movie. She's been like flitting around the universe, right, at like near the speed of light, come back to Earth and looks the same age. This can actually be explained very well using special relativity, because she's been travelling a lot at close to the speed of light.
Yeah, that's true. That's interesting.
Yeah, that's what.
And also how she keeps so thin.
Yeah. So that's
the real question is, how did you get that haircut?
So that's travelling forward in time, which mathematically and physically is entirely possible. Moving backwards in time is much more difficult to solve mathematically. So there have been lots of theories about it. No theories have been at all being able to be proven. It's just kind of pie in the sky ideas. So one professor, actually, Professor Ron Mallett, at the age of 10, his father died when he was like 33 due to a heart attack. And this young boy sort of vowed from that time on that he would invent time travel, go back in time and save his dad. Right?
Is this a true story?
It's an actual true story. Look up Ron Mallett. He's a theoretical physicist at the University of, I think, Massachusetts. So he's a professor at that university, teaches theoretical astrophysics, and has all sorts of theories about the possibility of travelling back in time. And it's all based on this theory of, black holes curve space-time, right? And we've all seen that kind of image of like this flat plane that goes into this like deep hole, where the black hole is, right, where like it's curved so much that you almost like can't actually see light going across a black hole. Now there's this whole idea that if you can bend space-time enough that space-time loops back on itself, there'll be a point where space and time cross over, and it's called making a closed time-like curve, so that if you're at one point in space and time, you could cross over the point where space and time cross over to go back in time. this is a complete kind of like mathematical, hypothetical what if scenario. But there's all sorts of theories about how you could make this. So if you imagine space and time was like on a piece of paper, and you rolled the piece of paper like a cylinder, if you created a very, very heavy mass and almost spun it like a cylinder, then you could cross over the cylinder, wrap around the cylinder, and come out at another point in time, like in the past. So there's all these ideas. Ron Mallett's idea is using like really, really high powered lasers, spinning them in a circle. So it's almost like if you took like a sticky pen on a big piece of fabric and like spun the pen, the fabric would like twist and curve back on itself round the pen. If you could do that with space and time and lasers, then you could try and find a way to cross into the past. So there's all these theories, but the problem with these theories are not only like mathematically the maths doesn't quite fit for it, but also if you're using lasers to bend space-time, for example, because energy bends space-time is like the way maths does.
Equals mc squared.
Yep. Then you would need lasers that are, I worked this out.
Death Stars.
Yeah, like
Julie,
more than 1,000 times the current strongest lasers, and you would need to bend them.
Do you have the power? I'm curious if we can measure measure of Death Stars.
So it's 30 megawatt lasers. Twisted.
Oh, Death Star's going more than 30 megawatts.
Well, like the most powerful laser we have on Earth is 30 kilowatts, and that can set fire to a vehicle a mile away.
It did
right?
what, sorry?
It set fire to a vehicle 1 mile away. And we would need lasers. So we would need lasers 1,000 times that strength, curving round the space, of our solar system, round and round and round.
So what was it? So okay, I have. Oh, wait, so actually, another quote: the sun is only 3 to the power of 26 watts. What did you say? Sorry, how many watts was the laser?
Oh, it's megawatts, so it's 10 to the 6 watts.
Okay, so that's like,
but in a laser rather than
that's so the sun has enough power for it. Apparently. Yeah, I mean, a lot. I can't unfortunately find the Death Star's power.
But then the Death Star Mark III that was in The Force Awakens took the power of a sun and blew up.
Do you mean Star Killer Base?
Whatever it was called.
Yeah,
it was...
not Death Star. That Mark II was already a thing.
No, that's why I said Mark III.
Oh, I see. No, it wasn't Death Star, it was Death Planet.
Death Planet
That's no Star Planet. Oh, here, what's the wattage of the Death Star super laser? The Death Star is actually on the same order of magnitude as the sun, so 6 to the power of 26.
That makes sense.
So that's what. So you in a Death Star wouldn't potentially warp time.
Yes, yeah, maybe it does actually. And
does that explain why the sequels are so terrible? The prequels, rather.
The prequels. So but you need to also curve it to warp space time in a curve, and you would need to curve that power of laser round the curvature of our solar system, or slow the speed of light down enough in crystals and stuff to about like 15 or 100 meters per second, and you could do that on the radius of the Earth.
The thing about all this time travel stuff, in my opinion, is it's incredibly hand-wavy.
Oh, it's so hand-wavy.
So maybe to give you a little bit of kind of background, both Steph and I have both studied physics. And, I have my PhD in physics, Steph has our engineering doctorate, so we're both kind of like knowledgeable these sort of things, and to some degree. and my experience is actually not as much time travel research as people might think, because it's so flaky, to be honest.
Yeah,
and
it's very
the
flaky.
truth is, a lot of people, physicists generally don't really believe that, and I've never met a physicist that actually genuinely thinks that time travel is legit.
I would love.
It actually causes a lot of problems with physics.
Yeah, that's exactly the thing, right? So physically, so imagine we did invent some magical thing that could send us back in time. What do you think that would do to physics, right? So my opinion is this, that because we are in an observable universe, if you go back to that same universe where you've been in the past, that's locked in time, right? So, and in space. So if you go back and observe it, you can't actually change anything. So this is because I'm obsessed with The Time Traveler's Wife, right? And I feel that that's the best depiction of time travel in fiction that I've seen, where one person is outside of time and he sort of can't control when and where he goes back to. But when he does go back, he's basically living that same scenario twice each time. Even if he thinks he's changing it, he's actually changing it to what already happened in his life. And so because everything has already happened in your past, when you go back, that past is now your future and you can't do anything about it. Right? So that's my opinion of time. And there was something else I was going to say about that as well.
Well, the thing that time travel sort of skips around a little bit, that no one I've actually ever heard it brought up, it suggests that the universe has a memory.
Mm-hmm.
And there's a little bit of evidence that this is indeed a thing. Because, if you know about quantum mechanics, you may have heard of a thing called waveform collapse.
Mm-hmm.
That when you measure a quantum particle, it gets locked into a particular state.
Yes.
And every time you measure that identical particle after that, it's still the same state. So this is a thing that I've heard called quantum consciousness, i.e. the universe knows you're looking at it.
Yeah, this is a weird thing because, particles at the quantum level can be modelled as waves, right? There's this whole wave-particle duality. But when you actually... But the sort of position and sort of momentum are linked by the Heisenberg's uncertainty principle, right? So they're linked by the Planck length or something?
I don't remember.
Basically,
H-bar, I think, from what I recall.
It's H-bar. So basically, yes, position and momentum. If you lock down the position of something, knowing exactly where it is, its sort of hypothetical momentum increases massively because you can't.
It's not hypothetical. It's exact. It's uncertainty.
It's uncertainty in it.
So if you know the position to 100% accuracy, you will know the momentum to 0% accuracy.
Yes.
And this is a function purely of fact. I don't know if you've ever seen this nice GIF, whatever, where essentially it's a function of actually summing up waves. Mm-hmm. So eventually you end up getting I think a Dirichlet delta function. You know what a Dirichlet delta is? You keep summing up, so you know exactly the position, i.e. this axis, but you know nothing of this. You just own, I think it's this. I can't remember exactly, but you know one thing exactly, but you know nothing else.
Yes. Yeah.
So yeah.
And that's where waveform collapse comes out of, isn't it? It's to do with that.
I don't know actually.
Okay.
Because that's all about. No, I don't think so. Because once you collapse a waveform, you know its momentum and its position exactly if you measure it. It's
really?
not. It's. I think so.
Oh.
You know, because it's not. That's how I understand it. Maybe talking crap, but once you collapse a waveform, any measurements yield the same result.
Huh.
When you collapse a waveform,
you know a lot more about quantum sort of field theory and stuff than I do.
Not really. I kind of failed that exam.
No one wants to know.
I'm going to look this up very quickly. I don't think it is a result of the Heisenberg uncertainty principle. Maybe it is, but as far as I understand, essentially what Wikipedia says is initially a superposition of several eigenstates, i.e. all the possible positions.
Right, okay, all possible positions.
It appears to reduce to a single eigenstate, which essentially is fancy pants way of saying one position, one state. Mm-hmm. It might be a result of the Heisenberg uncertainty principle, but I don't think it is, because all Heisenberg is essentially saying is you can know one state but not the other. Mm-hmm. You can know the other state but not what the other. And that's why if you ever get pulled over by the police, you can always tell them, "No, officer, I did not know how fast I was going, but I know exactly where I am." I'm actually not. I've never really thought about it too hard as into why wave function collapse happens. It wouldn't surprise me if it's actually not totally understood physically why this happens.
Yeah.
I'm looking at Wikipedia very quickly and I see no mention of Heisenberg.
Okay. Oh well.
But I suspect this is something that's actually... There is a few things in quantum mechanics that I think isn't understood physically.
No,
quantum mechanics is weird wiggly space-time.
Which is why in fiction it's always, you just shove quantum in the front of something and you can explain whatever is going on.
Quantum realm, jobs are good in.
Yeah.
The phenomenon is unrelated to the uncertainty principle.
I was wrong, you were right.
Although increasing precise movements of the operating position will naturally homogeneize the expansion coefficients of the wave. So, so it's actually unrelated. So essentially the uncertainty principle is just a result of waves.
But another scientific phenomenon that some physicists are looking into is this whole idea that if you flip a coin and it lands on heads, in another universe it's landed on tails, and that splits into like this kind of multi-universe kind of idea that there are like trillions of other universes there, that every time something happens by chance, then all those chances are possible, and so there is a universe where all those kind of different possibilities have occurred. Right?
I feel that a lot of this stuff is more science fiction.
It is science fiction.
There's not a lot of, at least I'm not aware of any serious research into the multi-universe other than,
It is a field of research, isn't it? Like, it's kind of linked in with, like...
cosmology, as far as I understand.
And, well, because for string theory to work...
Starting to get very philosophical.
Yeah, then it's kind of, then you need, like... There's like multiple dimensions in these sort of things, which I don't really know anything about, and I've
more
never
than
really
three
been
spatial
interested.
dimensions isn't weird though. That's a suggestion of multiple universes.
No, and it's a
we
mathematical
exist in a
way.
4-dimensional space time, but mathematically you can go to as many dimensions as you want. It really doesn't make a difference.
Yeah, and it's a way to make the maths fit some of the evidence or some of the theories, right? But,
well, I mean, we can build shapes in n-dimensional space, right? That's not a weird thing. That's something mathematicians do.
Because we live in a 3D space, we
can
find it
only
really
perceive
difficult to
4 dimensions, right?
Yeah.
X, Y, Z.
I struggle to even like perceive things in 3 dimensions. I remember when I was doing physics, I had to do like it was that kind of the molecule building one where we had to like, it was like crystal structures and stuff.
Yeah.
Young Heng that like taught us it, and he had like these little like anyway, it was structural physics, I think, and it was basically like crystallized structures. How many atoms are going to be?
Oh, the packing factors and crap like that. Yeah, I remember.
I struggled with that module so much because
I thought that was a gift.
like, a lot of people found it really easy, but I just really
a quarter of atom here, quarter here, across on the corners.
But I just really struggled to like in my head visualize things in 3D and like rotate them in my head.
Oh no, that's a skill that people can learn.
It is something you can learn, and like I'm very good in 2D because of my years of playing Tetris. Right? But see, if you had 3D Tetris, I would suck.
I think such a thing does exist actually.
I bet it does. I mean, 3D chess.
I struck at 2D Tetris. I can't imagine how terrible I'll be at 3D Tetris. Yeah, you're surprisingly good at Tetris 99.
Thanks.
Even won one time.
I did. I've only won once.
But you could win if you played more.
Yeah.
Anyway, this is definitely getting to the John Games podcast.
So, John, what was your second question then?
So, moving onwards, so as much fun as time travel is, this is more to my current field of expertise and very much inverted commas.
Yeah.
Again, by my friend Nikki, who asked, how legitimate is the AI threat, aka the Terminator?
Right, okay.
Which is kind of a hot topic at the moment, right? So,
very much so.
Now that I've finished my PhD in physics, I actually work in AI now. So this is kind of towards my area of work, I suppose.
Expertise.
It's a wee bit close to my heart as well because, it's my job as such. So
John's like express goal in life is to replace all humans with
computers.
computers.
Yeah, I mean, I must admit, the concept of humans with jobs seems very unsettling. No, of course, I have to have a job. If they could care if I don't do my job too well, then I don't have a job. Alright, so, I mean, in case for the younger viewers who maybe don't even know what a Terminator is, you think that's reasonable? Yeah, some of the younger people might not even hear it, because it was the 80s, right?
80s
actually,
and 90s.
Even before we were born, right?
Yeah, I mean, it was...
But, I mean, it was like 90s, it was still a thing, so...
Oh, yeah, for sure. I mean, I didn't watch Terminator until I was in my 20s, when someone older than me was like, oh, you've never seen the Terminator? Right, we're going down and watching it now. And
I've not seen it that many times. I didn't really remember that much about it. I've only
watched it once.
Funnily enough, I've got a funny story. When the first time I watched the Terminator on my own, it was accidentally on the exact same day as the Terminator. Not the year, but the same day of the year that the Terminator was set. It comes out like May 21st or something like that. And I was like, shit, it's May 21st! Anyway, so the kind of core concept of Terminator is, the gist is that some US government build this AI called Skynet. It becomes sentient and it starts like squashing all of humans because it determines that humans must be squashed. Mm-hmm. So Nikki was essentially asking, how plausible is that? Mm-hmm. And you probably heard Elon Musk also pointing out that he's like a bit worried about AI and nobody's taking him very seriously, and to be honest, I think quite rightly so. So when people say AI nowadays, there's very loosely two forms of AI. Mm-hmm. There's broad AI, general AI as such, and there's narrow AI. General AI is the concept that an AI can learn just about anything, which in principle it can. And the narrow AI is the idea that you build an AI to do one specific task. So a narrow AI would be when Facebook make an AI to recognize your face in a picture. That's narrow. It can only learn your faces. It's never going to learn anything else. And that's what 99.999% of AIs are. You know, if you want an AI to read some text, it'll only ever get good at reading text, nothing ever else. But there's this theoretical idea of general AI. It's very much in its infancy. Actually, recently, some company in England, London, I think, designed an AI that learned to play a game. I can't remember what game it was. It might have been like Mario or something. I don't think it was Mario. But typically, for example,
there is an AI Mario.
I know, but that's my next point.
Yeah, okay.
Typically, when you see these normal things like Mario and I.O., these are narrow, designed to play Mario.
Yeah, exactly.
But then if I showed it Zelda, it freaks out and doesn't do a good job, right? And that's narrow AI. But if you could design an AI that was, I could give it to any, like a human could give it to any general game and they could learn the game. If you could design an AI that could learn any general game, that's a general AI that could learn any game.
But then if you were to give that gamer AI a task of learning like faces,
well,
would it be able to do that?
Again, in principle, a general AI should be able to. But even in the terms of an AI that could just play video games, it's still a narrow AI. It's just a wider scope. Right?
But I assume that like the more AI progresses, the more these very narrow AIs are going to be given other jobs and other functions, and it's going to broaden their AI.
Yeah, exactly. So that's kind of what my second point was there, that this company in London actually built this AI that was generally just to play games. And I really think, at least to my knowledge, that is the closest we've came to a general AI. That's why Google bought them for an obscene amount of money, because that was the closest we've ever came to a general AI where you can give a problem to, of any description. And the AI will figure out the solution. Not because at the moment you give it a designed, very human, very focused problem, and it will learn the very focused problem.
I mean, yeah, absolutely. I mean, the way that humans at the moment speak to computers is giving a computer a job to do that a human would find quite difficult. So crunching hundreds of numbers, say, or processing lots of data, or taking lots and lots of things and having that kind of one function is what computers are very good at.
Well,
humans are not, right? So that's why we've kind of been why we're designing AIs to do this one
Well, actually, most AIs nowadays do tasks that humans can do very easily, for the most part. Like read a bag tag. That's 99% of the population can do that.
Yeah, we can all do that, but we can't read hundreds of bag tags.
Exactly.
Right?
That's
so
true.
It's the lots of data thing that AIs are very,
I
very
always
good
get
at.
triggered when people say computers are so clever. Computers are the most stupid machines. All they can do is add, minus. They can't even divide correctly.
Yeah.
Do you know that? I don't know if you're aware of that.
I think I've read that.
So if you do 10 divided by 3, the answer is 3 1/3. Computer says 3.33334. Or 2. It's wrong. It always gets it wrong. It can't divide. And this is an issue that does sometimes happen.
But is that because of it has to be a discrete number, whereas humans can visualize irrational numbers, right?
Well, exactly. A computer can only store a maximum amount of numbers.
Yeah. You could never have a computer
I think
know what pi is to infinity values.
Yeah,
right?
Well, exactly. I mean, I think there might be ways around it, but mathematically speaking, binary can't be has to be a irrational number. Rational. Can't be a fraction. Binary cannot be a fraction. It has
irrational
to be
fraction, because it can be a quarter.
No,
which is
binary actually
0.25.
can only be full numbers. Binary cannot be a decimal point.
No, because you just put the point as one of your binaries.
That's what you have to do. So a floating point number on a computer has the bit before the decimal point and the bit after the decimal point. The actual 1010 has to be interpreted by the computer, by a programmer later on to say that the first bit, there's two numbers here. The first number is before this point, the second number is after this.
So you have to tell the computer.
So no matter any way you want to swing this, you can't store a third as exactly 1/3.
Yeah,
it has to be to some arbitrary length.
Yeah, but you could store a quarter.
Yeah, that's fine. A quarter's fine because 0.250 to infinity.
Exactly.
That's fine. And it's always the things like a third that causes a problem.
Yeah.
But that's a wee bit beside the point, right? Okay, so essentially general AI, like Skynet, the AI that's going to take over the universe, is still very much a bit of a fantasy. There is research, but it's not easy.
Yeah.
But maybe we can but I'd say it's not easy. It's very much within potentially the realms of possibility.
Yeah, in terms of kind of they are allowed to make decisions, and the decision that they made was that humans are inherently bad for.
Whatever, I can't remember exactly
future.
the story arc, but it was something along the lines of essentially an AI is an optimizer. It optimizes a solution.
And I think that's exactly what Skynet was that they optimized the human condition and said, because of, war and hate and blah, blah, what humans have done to the planet and to themselves, the way to preserve life is to destroy humans. Right?
I think actually, I had a quick look at the Wikipedia very quickly, so I may have got this very wrong, but I think it was the AI, the people who made the AI realised that it was becoming too powerful. They tried to shut it down, and then the AI took that as an attack, and it destroyed the humans as a result. I think that's how it goes down. Yeah. I can't really remember the movie, because all we know is Arnold Schwarzenegger is back and shoots some people.
No, he will be back.
He will be back, yeah. Anyway, so the concept of AIs, becoming this powerful is not outside the realms of possibility, but it's quite a bit far. It's basically almost like saying, well, I won't bother studying for this exam because I'll just join Starfleet next week. Yeah, it's in the possibility, but it's not likely to happen in your time frame.
Right, well, hypotheticals aside then, if for whatever reason AI or some computer thing decided to destroy humans, how possible would it actually be, right?
Well, this is the next thing I'm going to bring up, actually. So, AIs in military use is not unheard of.
Yeah,
this happens.
For sure,
so, the first thing that I guess is I remember one of my colleagues went to a conference in London that I was about military applications, and funnily enough, the AI actually started to learn tactics that only the top generals kind of knew.
That makes sense. I could see
possible. The most optimal solution to a problem.
Yeah, especially if you're looking at tactically where the best places to attack would be, where the leads, the centers of say intelligence or military kind of defenses are. An AI could absolutely learn
So in this case, it was actually about submarine warfare.
Right.
Submarine versus a boat. And it figured out that the best thing to do was to sit in some very much blind spot of the sonar or something that it was quite not obvious.
Yeah.
So, it is used in military uses, but could a potential AI be used like the Terminator? And I think it's going to happen much sooner than we realise. Drone strikes has become the thing recently, and the moment that a drone strike works is someone sits 1 billion miles away and they control the drone, right? That is a very much AI capable or taking job, not a problem. All you need to do is image recognition. You've already got autopilots. This is not even like far away. This is like tomorrow.
I mean, this is happening. Not even military is normally 5 to 10 years more advanced than commercial applications, right? And it's happening in commercial applications, right?
The drones,
automated drones,
exactly. So the question is, how does a rope AI determine what to shoot at or not? That's getting messy.
Exactly, because
that's where it gets confusing.
If you're talking about, destroy as many lives as possible, not military or civilian, right? You'd have to teach an AI, whatever you want, right? If the tactics are to cause as much havoc as possible, i.e., a civilian as well as military lives, then an AI would learn that.
Well,
right?
interesting. Imagine you taught an AI, right? You need to kill the target. That's what you taught it. The AI goes away, okay, I will learn how to most efficiently. That's what this is actually not even really scare tactics. This is actually what the AI will optimize itself to the best way to kill that target.
And optimization is an odd one, because are you optimizing it for cost? Are you optimizing it for time? Are you optimizing
it's actually depending on how you design it. So for example, if you're designing an AI to read something, you would optimize it to be on its accuracy. So it depends how you wish to do that. You would probably optimize it. You would probably give it as many some scenarios and then optimize it on success rate. I mean, that's an example. You would be realistic. You'd have to be clever about this. You would have to do success rate versus unwanted casualties, etc. Because there's thing called an AI called the loss function. That is what it optimizes, and this loss function would be a sum of success versus how much fuel it used, how much ammo it used. Because I mean, if it had unlimited ammo, the probably most optimal one is just to shoot constantly, never stop, blow up everything. But realistically, that's not realistic.
Yeah, exactly.
So the interesting question is, ethically is that, because a person can decide, I'm not going to attack this target, it's beside 1,000 schools. The AI might decide, this is a good time for me to kill the target, even though it's beside the schools. It's still worth it. It doesn't, because the AI might not even realise a child is at that school. It just goes, go for it. And this is another concept, so I'm being on a wee bit, just my last point here. Another kind of thing that brought up with these self-driving cars is, how does the AI determine what decision to make? I.e., someone walks in front of the car while someone's behind them. Do you brake, hit the person behind you, hit them? Or hit the person in front? You know,
it's
that's
messy. It's a trolley problem, isn't it? You know.
I don't know, trolley problem.
Oh, the trolley problem is this kind of very well-known philosophical problem of, you have a trolley going down a track, right?
Oh, I think I know what this one. Oh, you mean this sort of trolley? Like a train trolley? Yeah, so trolley. I think it's supermarket. Yeah, I know what I'm talking about now.
So, the trolley is going down a track that's going to a branch. It's going to the left and killing a lot of people, right? Say 10 people. Do you pull a switch to send the trolley to the right-hand track where it's killing one person? Right?
I remember reading this as well, and the answer is pretty clearly the one person.
Yes, but you've made a decision that this life is, and you know, some trolley problems have it as, this is your sister or your son or something, right? It means that you have made that decision. You have physically done something that says that this life is worth the sacrifice for these lives, right? And like a computer probably would make that decision of,
most likely,
yeah, because you're optimizing the solution of you know, to save as many lives as possible. But is it ethical to actually change the course of things to still kill a life?
It's a complicated argument, and you know, we're not philosophy people,
but it's really important for not only the ethics but the laws and the rules of building AIs that have like people's lives in
when AI when an AI is in charge of taking people's lives, then that's its job. It's very messy, and it can be very easy to mess up.
Very easy to mess up. We need. I think that's Elon Musk's issue, is that lawmaking is very sluggish. Like, we're only just catching up in laws to sort of make the internet a more ethical place, right? And whether that's a good thing or a bad thing is like up, not for this podcast. But AI is moving, and the progression of AI is moving much faster than the lawmakers.
Most stuff seems to move faster than the lawmakers.
Yeah, and so we have this ethical problem of who's in charge and who's liable for if and when AIs malfunction and causes
not necessarily malfunction. Work perfectly the way they should be, but
work perfectly the way
sketchy ethics.
Exactly. So who's liable for that? You know what I mean? And I think that's something that like is what scares people, right?
That's the only concern I have with AI is that genuinely the drone strikes that are completely computer AI based is here. The technology is here.
Yeah.
I'm not worried about Terminator. Don't think that's very likely to happen anytime soon.
No, absolutely. And I think if all artificial intelligence that ever existed suddenly had this, say, bug that said, destroy all human life.
Actually, I don't think it would be a bug, though. That's the thing. It would be a feature, per
se. But how many robots are there in the world that could actually cause harm? Like, say I've got a smart toaster in my room, right? Or like, this was the classic XKCD, like, what if question. If I had, like, a smart toaster and a smart dishwasher and a smart TV, how much harm could they actually do to me? Like, really not that much, right?
Show you the Kardashians non-stop.
That would be a lot of harm.
So you kill yourself.
But absolutely, I think it's something that the ethics question is a really important question to ask. Yeah.
Yeah, well, we've probably waffled a bit too much about AI, so...
Yeah, so shall I go on to my last question?
Yes, I think that's a good idea.
Okay, so this question was asked by my friend Science Steph, and she asked, can a roach survive on Mars? So there's this classic thing that like cockroaches could survive a nuclear attack,
and
blah, blah,
Twinkies.
Twinkies. I'm not a biologist. I'm a physicist / astrophysicist by background and then now an engineer. So I don't know much about cockroaches.
They're gross.
They are gross, and
send them to Mars.
In some places they have wings and fly in your face. And
oh my god, really?
Yes.
Let's never go there.
In South Africa, I had a cockroach in my jumper when I was putting my jumper on. It flew right in my face, and it was like traumatized me for life.
Yeah, let's never go there ever.
But what I do know quite a bit about is Mars, and I've kind of broken it down into three things. So you've got where the atmosphere is habitable. So I'm talking about habitable generally, and you can then make a decision whether like cockroaches could habit in this, because I don't know anything about cockroaches. I've talked about water content on Mars, because all life needs water, and then the kind of other food, vegetation, mineral stuff on Mars, right? And I put the three in the kind of order of how much I know about them. So atmosphere I know most about. Life, food and vegetation I know least about, right? So let's talk about the atmosphere first. So Mars has a really, really thin atmosphere. Like it's about 100 times thinner than it is on Earth.
Oh, I don't know if
so yeah. So the pressure.
I was under the impression. I don't know. Actually, under the impression. I thought Mars had an atmosphere, just not breathable.
Yeah. So Mars has an atmosphere, but so Earth's atmosphere is like pretty big by any sort of estimation,
yeah, I suppose
right?
so, yeah.
But the sort of atmospheric pressure that you'd feel on Mars is about 100 times smaller than on Earth.
Okay.
And that's because of various reasons. It's mostly because Mars is less dense and less heavy than Earth. Mm-hmm. So its gravitational pull is about a third of that of Earth.
Is it really that small?
It's really quite small.
I didn't realize it was that small either.
Mars' diameter is about half that.
Yeah, I knew Mars was small. I didn't realize a third of this.
Yeah.
Gravity,
so it means that basically, when you've got a low gravity, what you have is easier to escape the gravitational pull, and what you've got is escape velocity, right? So you need to get to a certain speed to be free of the gravitational pull of a planet, right? And so the escape velocity for Mars is much smaller than on Earth, because I think these things scale by the square, right? Which means that while Earth has like a really nitrogen, oxygen-rich atmosphere, those elements are pretty light, and so just are going too fast for Mars. So there's no nitrogen, very low amount of oxygen, and actually 95% of the atmosphere of Mars is made of carbon dioxide. And so really, for anything that's like living on Earth, it's like not breathable, right? Things would die. There's a fraction of a percentage of oxygen in Mars's atmosphere. And then also another reason why the atmosphere is so thin is because a lot of it's actually been blown away by the solar wind. So what happens is solar wind is basically like a very, very high energy radiative wave, which ionizes particles. And what we see with the solar wind is like very ionized particles making the northern lights. Mm-hmm. So the ionization basically kind of lights up the northern lights, lights up the sky. And that ionization force breaks apart the carbon and the oxygen. So the carbon dioxide is 1 carbon, 2 oxygen, right? Mm-hmm. And it breaks apart that. The oxygen kind of floats away, and the extra kind of electrons from the carbon fuse again with the carbon, and you've got like lots of heavy enriched carbon. So it's like carbon 13, because carbon's normally 12 electrons, but you've got a lot of carbon 13 in like on the surface.
Isn't it the protons? The atomic number.
Yeah, so it's the enriched carbon though, so it's got the extra proton.
That would make sense.
That would probably make sense, yeah.
Stabilized up with a nuclear containing 6 protons and 7 neutrons. That is up to 13.
Yeah.
So it has an extra neutron apparently.
Okay, so but it's using those extra particles from the ionization and fusing together. So that's why you've got all this kind of enriched carbon on Mars, and that's from the solar wind as well. So atmosphere, not breathable, very thin. So I don't think a roach would survive just on the atmosphere alone.
Apparently, a roach can survive without the air for 45 minutes, according to the Wikipedia.
Oh, wow. Well, there you go.
The best resources for your degree.
So maybe a roach would survive for 45 minutes.
Although, I wonder how long a roach would, because we're talking basically human terms here.
Yeah.
Roach needs a tiny amount of oxygen compared to a roach. I mean,
but I don't know how much it would survive, because roaches breathe, right? How much they would survive breathing in all that carbon dioxide.
Oh, that's true.
But maybe like vegetation might survive if we were to plant that, because they...
Yeah, maybe. I'm not sure. I don't know enough about biology to say, to be honest.
Not a biologist.
Yeah, that's it.
So then in water content, there is liquid water on Mars. The problem is that the one evidence of liquid water that we found on Mars is under the southern ice cap. So there's like a shit ton of frozen ice, like ice water on Mars at both of the caps.
That's puppies.
Yeah, because these lakes are like 4 kilometers deep. So it's like basically almost the height of Mont Blanc in the Alps, deep.
Oh wow, yeah,
ice, right? So there's loads and loads of ice. There's as much ice, I think, in the northern ice cap as there is on Greenland in Earth, right? Which is pretty massive for Mars, right? And underneath the southern ice cap, there is evidence of a big liquid lake that was sort of multiple kilometers wide. But to survive there, where there is liquid water, you basically need to survive. So like on Earth, at the poles, you get like 6 months of darkness followed by 6 months of light. So you basically need to survive 6 months of darkness in a very low atmosphere. So like very, very, very cold, with like frozen CO2, like a big thick layer of frozen CO2 that when it starts to melt and turn back into gas at springtime, it basically causes these big massive gas plumes and like big like explosions of dust and everything. And it's like, super volatile. So like you basically just would have to survive in the Arctic, like on Earth, but on Mars.
So there has been research into how long cockroaches survive the cold. Called the Japanese cockroach, which hibernates in cold winter, survives 12 hours at -5 to -8 in laboratory experiments, which I'm guessing is probably the bottom end of how long they can survive.
Yeah,
I'm guessing Mars is colder than that.
That's not very cold. Like, that's
Mars, don't really, it's like Scotland weather.
Exactly,
sometimes.
like -5 is warmer than
Well, we don't get cockroaches in Scotland, do you?
Yeah, we do.
Really? Where?
Like in people's homes, in like dodgy flats in Glasgow, you get cockroaches.
Never even seen one.
What? Really? I had a flat in my second year of uni that was gross. I don't know if you saw it, but like there were all sorts of bugs and there were definitely cockroaches there and it was horrible. So yeah, we get cockroaches here.
Used to get them bad in Honduras. A ton of them in Honduras.
Oh, really?
Yeah, they would.
Whoa.
But the thing is, they would spray the floor, so they just die and be dead everywhere. I'm like, this is gross. This is the worst.
But no, I can't really remember the number, but I think Mars winters at the poles get down to like -20, -30 C at least. And that's
I thought it would be way colder.
It probably is colder.
Yeah, whatever. I mean, it's pretty damn cold.
Yeah. And in terms of like other life, food and vegetation, there's like none of these things, right? So there are lots of mineral deposits on rocks. So Mars, the reason it's red is because it's basically these kind of iron oxide deposits, which is like basically rust, right? There's loads of rust. If a cockroach could eat rust, they could be alright.
Again, this Wikipedia article has like got a little bit of hot cold hardiness. That's where I'm getting all my knowledge from. So apparently some species are capable of being active for a month without food and can survive in limited resources, like the glue from the back of postage stamps.
Really?
Yeah. Nothing about like surviving Mars with minerals, but
well, maybe. Oh, I think a roach could certainly survive longer on Mars than a human could.
Definitely, yeah.
Definitely. I don't think you'd be able to get like a roach colony that like actually survive on Mars.
I don't think so, yeah.
But for humans to survive on Mars, what we would need to crack are 3 things. So we would need to crack agriculture on Mars, right? That's the first and most important thing, is to maybe have like some sort of biodome or something, but crack growing plants and agriculture on Mars, right? Because that would give you the oxygen-rich atmosphere that you need, and be able to like you'd be able to recycle a lot of waste using agriculture as well. The second thing we would need to crack is just like surviving the dust storms and the ionization and like all the things you get with like harsh atmospheres, because you need to protect yourself from all the sun's rays, basically like all the like UV and everything that our atmosphere protects us from. Surviving on Mars is it's possible.
It's challenging,
but extremely challenging, and with today's technology and stuff, it's just not feasible. Like a lot of people are saying, oh, we screwed up the Earth and like climate change and everything's going to destroy the Earth, so let's just go live on Mars. It's like, mate, we're not going to see that in the next 50 years. Like, I'm not going to see a habitable colony on Mars in my lifetime.
Probably not.
Maybe right at the end of my life, if I live till like I'm really old, we might see like the first long-term colony on Mars. But all these calls of like, oh, go to Mars. It's like, it's a one-way trip. And
at the moment, it's a one-way trip. Yeah, for sure.
the technology isn't there. Like, it's possible. It's definitely not out with
We could
realms
get
of
things to
physics.
Mars, we just can't get them back.
Yeah.
Matt Damon, if he gets stuck there, he ain't coming back. He will go after those cockroaches.
He'll eat them.
Yeah, he is well renowned, I imagine, for murdering cockroaches.
Good. So I think that's our questions.
Yeah, I've done mine too. You've done your two.
Yep. So if you have any questions, and you're watching this on YouTube, then leave your questions in the comment section down below. If you're watching this in your usual place that you get podcasts, then follow me on Twitter. I'm at Sci with Steph, because that's Science with Steph. So follow us on social media. Maybe just ask me a question, because John is
probably the best. Yeah.
And we'll look forward to hearing from you, and we'll see you in the next episode.
Thanks for listening.
Bye.
Bye bye.